Hi, this is a video for the third FEM lab, and in this video we'll be making the simulation and get results from the simulation. So in the slides we actually provided a benchmark value, so if you get your results within 10%, that would be very good. So the content for today is we need to check the FEM before we go into the sim, and we'll create gluing and contact in the simulation. Okay, so the gluing is to connect the upper jaw to this jaw handle and to the 2D portion of this handle. Then the contact is for the sliding block to slide on the handle, as well as the lower jaw to slide on the handle. Then we'll create loads and constraints. Then we will modify the output so we can get force out of the C-bushes on the hinges. Then you can compare the value to your hand calculation. Okay, then we'll show you the proper results. Then the last is some troubleshooting, just in case you got some error message, and how would you deal with these errors. Alright, so the first thing you need to do is to check your FEM model. Okay, so I have everything here. Just let me delete the force. Delete all. Have a clean simulation. Or I can just create another one. So I'll close this sim. And I have a FEM, which is what you should have. You should have the FEM, and you want to check show adjacent for the joints, for the pin joints and the ball joint, and check the element edge for the upper jaw, because there are two pieces. Just want to make sure they are merged. The materials thickness for the meshes. Basically, all these things are the, right click, edit, then go into your property and look at the material, if they have material, or if for the 2D you would want to check if they have material and the thickness. Then for 1D you have a little bit more. For the bars you want to check the force section, the material, these two, and for the C-bush you want to check the stiffness. Okay, so this one is the ball joint, and inside of the C-bush collector you need to right click on the mesh itself and check this data, associated data, to make sure you have the coordinate system override enabled. Okay, so that's all the basic things, and you should have them done in the last lab. Here we're going to talk about the show adjacent check. Okay, so let me hide everything. So we made all those joints, and how do we know if they are correct or not before you run into the simulation? Okay, and for this we will need to do a show adjacent check. We will hide all the elements except the one on the top. So we're going to check this pin joints first, and what you can do is you can box select the bottom ones, and we have hide command. You can do Control B as a shortcut, as well as this C bar. Just leave the top one alone. Now we have only the top one on the screen, then we will use this show adjacent command. The show adjacent will display, as you can read here, it will display the elements that's directly connected to the one you're going to select. So let's turn on the command and select the top spider, and once you click apply, it'll show the elements that's connected on those nodes. They share nodes with this spider. So we do apply. You can see those are the 3D elements that's connected on the spider, and the C bar is also connected on the spider. So now we will do a show adjacent for this C bar. And this is the most important step in this whole show adjacent thing. Okay, so from here, remember we had a spider that will rotate on the C-bar. And if you do a show adjacent, you do not want to see that spider. Because if it's showing up, that means that spider is directly connected on this node, meaning it's welded and it will not rotate. So if we do apply, you should only see the C bush showing up. So from the C bar to the spider in the middle, you would have a C bush in between. So now the next step, if you show adjacent for the SP, you can see the spider in the middle. So all the check is really for this from C bar to SP to spider. Okay, and sometimes, occasionally, people would have errors from, say, C bar to the bottom spider, from the bottom spider to the mesh, but that's rare. Most common error would be from the rotational joints. So that is done for the pin joints, and the display will become weird. You can either do undo to go back to this stage, or you can also do a show and then hide, something like this. It'll bring everything back. And this one is also a pin joint, so we don't have to do that. And you should check every single one of them, just in case it's not right. And this is a ball joint. Okay, between two spiders, there is a C bush. So I'm gonna hide the C bush. I'm gonna do Control B. I need to pick this SP as well, or simply just uncheck the C bush collectors. Okay, so I have one side of the spiders on the screen. Now I'll do a show adjacent for the spider. Apply. Now that means it's connected to your solid, and it's connected to the SP. Then we select SP, it'll show the other side. So this is a good connection. And the element edge check, we did that last time, so we're gonna skip that. Then we'll, after all the checks, okay, let's talk about something for the materials. It might be hard to, tedious to get into your collector and show a monkey wrench. We can actually change the display of this navigator by right click on this name tab and change it to material view. So this way everything will be sorted as material. So you can see we have steel. Pretty much all the whole thing is steel, and the nylon is only this bar here. Okay, no material. That is a polygon, and also the spiders and the C bush. They don't have material. If you turn them on, it'll be like this. So we can switch back to a standard view, which is sorted by 1D, 2D, and 3D. And there's also a physical property view. You can take a look. The P shell, P solids. So sometimes it's useful. Let's see. P shell 1, different thickness, right? Just double click. It'll show the information of that property. It's 0.125 thickness, and the material is steel. So those are the three different views that you can use for the this navigator. Usually we just stay here. Now the next step, we will create a simulation. So you should have the same already in your folder, and I'm gonna create a new one. Simulation. Okay. Alright, now in the simulation we need to define the contact between these blocks, and we need to glue the the jaw handle together from the 2D to 3D to the upper jaw. They should be a single piece, which we separated in the CAD and in the fan. So the first thing is gluing, okay, which is one of the simulation objects. So in this manual is for simulation objects. We have surface-to-surface gluing. We also have surface-to-surface contact. So the first thing is gluing. And what you want to do is do a manual glue from the source to target. And usually you want the source to be the finer mesh. And we have the same size, so it doesn't matter. And we have no region right now. We need to create a new region. We're going to glue this piece, okay, this surface to the surface on the handle portion. So you can't really pick the face here if you click. It's an element. So I want to pick all the nodes on this face. We need to use a method which is feature angle element face. And at this stage you should be familiar with this name, feature angle element face, and the other one is feature edge nodes. Okay, feature angle element face. We'll pick this face, and it'll go all the way to a corner that's less than 30 degrees. Larger than 30 degrees. And this will be a region 1. You can also rename that. I'll say this is glue 1-1. Okay, top surface. The top surface for 3D Tetra by default is the outside surface. Okay, and say OK. And I'll glue this to the face here, and it's got blocked by the upper jaw. So I'll expand the fan here, expand 3D, and hide the upper jaw. Then we can select this face. Again, using the same method, feature angle element face. This region, and that will be glue 1, 2. So we have the first glue 2 regions, and the search distance, usually you don't have to change that, okay, unless your model is a little bit separated. So that's we don't have to talk about that. We do apply, so we can go ahead and create another gluing, right? And that is the display of your glue. It'll search from those arrows to those arrows. So 2 regions, they're trying to find the other region within this search distance, and the load will be transferred between them. And before we start the second glue, you can take a look in the region. Those are the 2 regions we just created. So it's not necessarily you have to do the glue and create the region while you are doing it. You can actually create a region before you started gluing. So also in this object, simulation objects, that's our gluing. So this one. Sometimes you can hide it. Okay. So what I'm gonna do next is I'm gonna create a region first for the glue that's happening here. So I'll hide all 3D to pick this one first. And remember, we did a 2D normal direction. And for 2D mesh, it really matters the top or bottom surface. So this is the second glue, the first portion, the first region. And I'll use feature angle element face. Pick this. You have 2 pieces of mesh. And you know which side is top, which side is bottom. The normal side is the top surface. That's why we reversed the normal of one of these meshes. And if you are not sure, you should go back to the FEM and check the normal direction of them. So we want the top surface and apply. Okay, so that is the region on the 2D. We'll hide this, show 3D, and we'll create a region on the 3D for the second glue, a second region, and okay. So we have those 2 regions. Then we'll keep creating the regions for the contact, which is here from this side to the lower jaw. So we'll create a new region. Now this time it's a contact, first region, and I want this surface, and see what happens if we use the default tolerance here. So feature angle element face, click this. As you can see, it goes all the way to the bottom, which is too much. So we'll deselect first, then we'll change the tolerance for this filter or the method to 5 degrees. This will reduce a lot of the selections. So we only have this one. And somehow this is still displayed, but as you can see, if we deselect, there's nothing selected. So maybe we can do a refresh. I'll just ignore that. And that's contact 1, apply. We'll do a contact 1, 2 for the lower jaw. So we're going to hide everything except the lower jaw. And then we need to pick this cylindrical face. Then that angle is still at 5 degrees, so it will not go all the way to the bottom here. You can just click a second time. You should be able to select that. Okay. Then we'll say this is a contact 1, 2. Apply. Then we'll hide this, show this piece again. Now this time it's the back side, which will be contact with the stopping. It's actually a sliding block. Okay, so the naming doesn't really matter. There's contact 2, 1, and the stopping contact sliding block, contact 2, 2. Okay, so we have all the regions done, and if you want to, you can turn this to maybe this thing here. Then you can select the region, and I'll just hit downwards key. You can see all the regions where they are. Okay, just to verify you created them correctly. Then we have one gluing done. We'll create the second gluing, which is this one. So surface to surface gluing, manual. We'll do glue 2 to glue 2, 1 to 2, 2, and OK. Then we'll do contact, surface to surface contact. Again, that's manual. From contact 1 to contact 1, 2. Apply. And you can see those arrows showing up. Contact 2, 1 to contact 2, 2, which is on this side. And you notice we have the option to input a coefficient of static friction, but we don't do this right now. It's an ideal situation, no friction. So we'll say OK. And those are the gluing and contacts. Sometimes if you want to make them smaller, they look nasty, you can change them a little bit in the display. Okay, so something like this. Then the next step is boundary conditions. First is the load. So we want to apply the load on the symmetry plane, which the 2D mesh is already on the symmetry plane, and only this side you want to pick a node on the symmetry plane, which is in the middle. So we're not sure if the node in the middle is really on the symmetry plane. What we need to do is go back to the FEM, and in the FEM we have a tool in edit, node, and modify coordinate. Okay, you can zoom in, pick a node in the middle. So I have the node ID here, 4809, and yours probably will be different. So I select the one here. You can see the Z coordinate is 0, so that means this one is on XY plane. This node is good, and I will apply the force on this node. So you want to remember this ID, okay, this node ID. on your model. So my model is 4809. Your model might be different. But once you remember the ID, you would be able to find it. Then apply a force on this node. Okay, that's the number I remembered. 10 pounds. And the direction we want to apply from this node towards another handle. So that's the direction you want the two forces to be equal and opposite, so they can cancel out themselves. Apply. So this is the first. The second, you want to pick the same node, 10 pounds, 2 points for the direction from the same node to the one you just apply the force on, or the node you remember the ID. So okay. And sometimes it's hard to see if they are really exactly opposite. So what we can do is we can select both, right click on the information, and we have the force direction here as a vector. Okay, so you can take a look at the vector. You should have the same number opposite signs, and ideally you should have 0 on the z direction. That means they are in the symmetry plane, in plane force. Okay, and that's for the force. The constraints, we have 2 types of constraint. The first constraint is easy to visualize, the fixed constraint for the model in the center of this nylon bar. Okay, so that one's here. So once you have fixed constraint, we apply force, you squeeze it, the 2 jaw will come together towards the center. And the second constraint will kill degree of freedom 3. And this is not in the real life. In real life, this is enough to squeeze your pliers. But in a simulation, there's a mechanism here which he will talk about in the class. The tetras, these things, they don't have degree of freedom 4, 5, 6. So you do a fully fixed constraint here. Once the constraint transferred into 3D tetra, they don't have rotational degree of freedom. So that means those 3D tetra are free to rotate on 4, 5, 6, even though you've killed all 6 degrees of freedom in the C-bar. So how do we stop it from rotating on 4, 5, 6? And this is fixed. These can rotate. That means these can rotate on the C-bar. So we just kill the Z direction on this structure, on the handles and this little block, because this little block has no contact to the other meshes. Okay, only has a ball joint, so which will not stop rotating anyway. And for that, we needed to use user-defined constraint, kill degree of freedom 3, and pick at least 3 nodes on each of these 3 parts. And those 3 nodes should not be in line, so you don't want to pick these 3. This will not stop rotating because they're in line. So you want to pick that. You can pick more. Right, these. Pick some more here for the other handle, and also you can pick some on the sliding block. So I'm gonna hide the lower jaw here and just pick some node, and you can take a look what I just selected. Hide simulation objects, and those are the nodes. When we say OK, you can see the constraints. So with these, this model will run. Without these, your model usually will not run. You would get a no results error. And if you force the NX to run through it by the method at the last page, you will see a huge displacement on the handle. It's rotating on the C-bar. If you like, you can actually disable them and try to run it to see what happens. So we're good on the constraints and on the force. Usually you want to do a model setup check. So the warning is fine because we have too many solids, and there's also this one. And another thing is you can run the model now, but we want to get the force out of the C bushes. So we will create a group. Okay. So what you can do is you can right click this group here, create a new group, and it's a group for the meshes or for the elements. So we want to choose all the C bush plus the nylon bar. So in my case, my nylon bar is made as the last. In your case, you might have the nylon bar on the top. So you don't have to hold down any key. It's automatically multi-select. So I have all this 4 SP and 1 nylon bar selected. I'll say OK. Okay, so in this output group, I have this group with 5 meshes. Then how do we enable them? So we do a solve, edit the attributes, and the case control output request, monkey wrench. Then in this, usually you can enable the SPC force to print. Right, so print. And for the forces in the C bush and the C nylon bar, you want to enable the force tab. Change to print. Change the entity to just the group. We don't want the whole model to show up in FO6. And in group, we choose this group. Okay, and you can also create a group here, the same as you right click here and create a new group. And OK. So we just ask NX to write the forces of the C bush into FO6. Now we can do a solve. And if your solve didn't went through, you should look at the last 2 pages for the troubleshooting. Okay, first the troubleshooting is no results. That means you don't have enough support most of the time. So you can turn on a parameter to force NX to run, and run the animation in results. You can see something will break. And the other situation is you get an error message. When you do a model setup check, you probably see one of these, and you can fix them accordingly. Then here's the results. Okay, so it's running a pretty long time. Let's see the results. In FO6, you will find the force in bar elements. That's in the group we just turned on. So the axial force is the force along the C bar, which will be about 22 pounds. So you squeeze 10 pounds on the handle, you get 22 pounds in the jaw, right? Then the forces in the C bush elements, that's the force in the joints. And you will be doing hand calculation, then get values compared to those values in the FO6. Then that's the displacement magnitude. You should have a number within 10%. Okay. So the job is finished. Close. Okay. Take a look at the displacement. And also, for your report, you would like to add your name here, so it looks nice with your name on your work, right? So we can do a right click for the post view and edit. And in Legend, you can change the header from automatic to customized, and click this button. You can add a line here to add your own name or whatever you want to add, and say OK. Now you would have the last line, okay, with your name. So we will be asking you to put your name in the plot to prove this is your own work. Okay. And also you will need to submit the FO6 file. So talking about FO6 file, let's see where's my FO6. So my model is for FAM3, FAM1, SIM1. Okay, FAM1, SIM1, FO6. Yeah. So FAM1, SIM1, that's this one. Then we'll open this in Notepad. Go to the bottom. Then go up a little bit. Then we have the force in the bar element. Axial force in C-bush element, that's the forces in the joints. You would have two C-bush that has the same numbers. Okay, as to why you would learn that in the class, because the link is a two force member. So on this joint and this joint, you would have equal and opposite forces. So those two C-bush are the two C-bush here. Okay, and you have one C-bush that has 3 zeros on degree of freedom 4, 5, 6, which means that's the ball joint. So that one is between the sliding block and the handle. So the only one left is from the handle to the lower jaw. Alright, and I think that's all for the simulation portion. We might have another video for you to get the stress inside this piece. Alright, thank you very much.